Dividing radicals can feel, well, a little messy. But what if we thought of it like climbing a ladder? Each rung is a new skill, a new step that gets us closer to the top, a perfectly simplified answer. It might look complicated from down here, but we're going to tackle it one rung at a time. So, take a look at this. 5 divided by the square root of 3. It seems about as simple as it gets, right? But in math, this isn't considered, well, finished. It's kind of like leaving your shoes in the middle of the floor. It's just not tidy. So what's the actual rule being broken here? The problem is this big, fundamental rule of mathematical housekeeping. You are just not allowed to leave a radical in the denominator of a fraction. It's considered unsimplified. That's it. That's the entire goal of everything we're about to do, to just sweep that radical right out of there. And this whole tidy-up process, it's got a formal name, root rationalization. It's just the technique we use to eliminate those pesky radicals from the denominator. So seriously, whenever you hear rationalize the denominator, just think, okay, time to clean up the bottom of this fraction. All right, let's step onto the very first rung of our ladder. This is simple division. This is where the numbers are going to play nicely together. It's really the most straightforward kind of problem you'll ever see with these. The easiest case, by far, is when the radicals have the same index. That little number tucked into the check mark of the radical sign. If you're dividing a cube root by another cube root or a square root by another square root, the process is super direct. You can probably even guess what to do. And this table just breaks it down perfectly. Check out the example. First, you deal with the coefficients. Those are the numbers hanging out outside the radical. Just divide them like normal. 4 divided by 2 is 2. Easy. Next, you handle the radicands, the numbers inside the radical. Since the indices match, you can just divide them directly. 6 divided by 3 is 2. Then you just combine the two parts and you get your final tidy answer. 2 times the cube root of 2. Okay, time for the next rung. So what happens when the numbers don't divide so cleanly? This is where the real work begins. We're starting with what are called monomials, which is really just a fancy word for a denominator that only has a single term. So let's just be crystal clear about our goal here. Our one and only mission is to get rid of that radical on the bottom. And to do that, we need a clever little trick. And here is that trick. We're going to multiply by 1, but it's a very specific, kind of clever version of 1. If we have the square root of 3 on the bottom, our clever 1 is the square root of 3 over itself. This doesn't actually change the fraction's value, right? It just changes its appearance. Now watch what happens in the denominator. Root 3 times root 3 gives us the square root of 9. And what's the square root of 9? It's just 3. And like that, poof, the radical is gone. This slide really illustrates the why behind that trick. Think of the radical sign as a jail. For a square root, which has that invisible index of 2, a number needs a partner to escape. That's why root 5 times root 5 equals 5. But for a cube root with an index of 3, you need a trio, 3 of a kind to break free. This is the key to everything that comes next. So let's apply that idea. Let's say we have 1 over the cube root of 2. To rationalize this, we need a trio of 2's under that cube root sign. Right now, we only have 1. So how many more do we need to make our trio? We need 2 more 2's. So our clever 1 this time is the cube root of 4 over the cube root of 4. Why 4? Because inside the radical, 2 times 4 is 8. And the cube root of 8 is a nice, clean 2. The trio is complete, the radical disappears, and we're just left with the 2 on the bottom. Mission accomplished. Okay, we are moving on up the ladder. We've handled simple division, we've handled single-term radicals. Now it's time for a brand new tool to handle a trickier situation, binomial denominators. So look at this problem. The denominator isn't just a simple root 2, it's 4 minus root 2. It has 2 terms, which makes it a binomial. And this changes everything. Our old tricks just aren't going to cut it anymore. I mean, why not? If we just multiply by root 2 over root 2, we'd have to distribute it to both terms in the denominator. We'd get 4 times root 2 minus 2. You see, we got rid of one radical, but we just created another one. We're just chasing our own tail. We need a more powerful tool. And that tool is called the conjugate. It sounds super fancy, but it's incredibly simple. To find the conjugate of a binomial, you just take the exact same 2 terms and flip the sign in the middle. So the conjugate of 4 minus root 2 is 4 plus root 2. That's it, seriously.
So here's the game plan. You find the conjugate of the denominator, and then you multiply the top and the bottom by it. Yep, our clever one trick again. Now, when you multiply those two binomials on the bottom, something kind of magical happens. The middle terms, the ones with the radicals, will always cancel each other out, leaving you with a clean, rational number. And this isn't just random magic. It's mathematical magic based on something called the difference of two squares. When you multiply an expression like a minus root b by its conjugate, a plus root b, you are guaranteed to get a squared minus b. The square root gets squared away, and the radical just vanishes. It's beautiful. Now, a quick heads up. After all this hard work, the final answer can look surprisingly messy. One of our sources had the absolute perfect description. The result almost looks like roadkill. It might actually look more complicated than what you started with, but just look at the denominator. If there's no radical down there, it is officially, by definition, simplified. And here it is, the single biggest trap in all of algebra, so please listen up. As this slide shows, you can only cancel common factors. That's things being multiplied together. You can never cancel common terms. That's things being added or subtracted. Trying to cancel the 3's in 3 plus x over 3 is the most common mistake you can possibly make, and it will give you the wrong answer every single time. Don't do it.
We've almost reached the top of the ladder. This is the final challenge, the one that combines several of our ideas. So what do you do when the radicals are dividing don't even have the same index?
Yeah, look at this. The square root of 6 divided by the cube root of 2. We've got an index of 2 versus an index of 3. They're not even speaking the same language. We can't just divide them. We need a way to make them compatible, like a mathematical Rosetta Stone. And this is our 4-step path to the top. Step 1, we convert the radicals into fractional exponents. So the square root of 6 becomes 6 to the 1/2 power, and the cube root of 2 becomes 2 to the 1/3 power. Step 2, we find a common denominator for those fractions, 1/2 and 1/3. In this case, it's 6. Step 3, we rewrite our expressions using that new denominator. So 1/2 becomes 3/6 and 1/3 becomes 2/6. Finally, step 4, we convert them back to radical form. Now we have the 6th root of 6 cubed over the 6th root of 2 squared. Look at that. They have the same index now, and we can simplify just like we did way back on the very first rung. So there we have it. We've climbed the entire ladder. We've seen that what looks like mathematical roadkill is really just a simplified, tidy expression. You now have a complete toolkit for dividing any kind of radical that gets thrown your way. The only question left is, what mathematical mess are you going to go tidy up next?